Ever stop to think about how your computer can stream music, browse the web, and download a file all at the same time without just crashing? It's all thanks to this hidden digital ballet called process synchronization. And today, we're going to pull back the curtain.
Now, I know that sounds like the setup to a really weird joke, but the answer is actually a beautiful solution to a super complex problem. Stick with me and you'll see exactly how the simple act of waiting in line at a bakery is the key to creating order from digital chaos. So think of your operating system like a really strict security guard. It builds these strong walls between every single program to keep them from messing with each other. But sometimes programs need to cooperate, so they agree to knock down a tiny piece of that wall and create a little common area, a shared piece of memory where they can talk.
And this is where the trouble starts. You see, when you knock down those walls, you introduce risk. If two programs try to change the same piece of info at the exact same millisecond, well, the results can be unpredictable and honestly pretty disastrous. This is where the chaos begins.
Okay, to really get a handle on this, let's look at a classic computer science problem. It's called the producer-consumer problem. And believe it or not, it's happening constantly, right inside your web browser.
The idea is pretty simple, right? A web server produces a web page, and your browser consumes it. Now, to manage that data transfer, they use a shared temporary storage space. We call it a buffer. The server fills up the buffer, and the browser empties it out.
Now, for this to work, both the producer and the consumer have to agree on one thing. How full is the buffer? They keep track using a single shared number called a counter. When the producer adds an item, it increments the counter. When the consumer takes one out, it decrements it. Simple, right? Well, not quite.
Okay, so let's picture this. The buffer isn't full, but it's not empty either. Let's say our counter's value is 5. Right now, the producer wants to add an item, so it needs to run counter plus plus. And at the very same instant, the consumer is ready to grab an item, so it needs to run counter minus.
So what should the final value be? I mean, you add 1, you subtract 1, the counter should go right back to 5. That's just basic math, isn't it? Well, in the lightning-fast world of computers, it's not that simple.
You see, here's the catch. A simple command like add 1 is actually made up of several microscopic steps for the computer's processor, and the timing of those tiny little steps can overlap in really weird ways. This means the final value of our counter could be 4, 6, or the correct value of 5. Two of those three outcomes are just plain wrong, and that's how you get data chaos.
This whole mess has a name. It's called a race condition. It's when multiple processes are literally racing to access and change shared data, and the final result completely depends on who gets there a microsecond before the other. This is the big bad villain we need to defeat.
So to take down these race conditions, computer scientists had to come up with a set of rules, a protocol to manage who gets to touch the shared data and when. The part of the code that actually touches that data is called the critical section, and the challenge of protecting it is the critical section problem.
Any real solution has to follow 3 non-negotiable rules. First, mutual exclusion. Think of it like a bathroom stall. Only one process gets to be in the critical section at a time. Second, progress. If the room is empty and people are waiting, you can't just freeze up. A decision has to be made about who goes next. And third, bounded waiting. You can't let a process starve, waiting forever while others keep cutting in line.
Okay, try to solve this for thousands of processes right away is tough, so let's shrink the problem down. Let's imagine we only have 2. We'll call them P0 and P1. We're going to try a few ideas and see just how tricky this really is.
All right, attempt number 1, let's just make them take turns. P0 goes, then P1, then P0, and so on. This definitely solves the mutual exclusion problem, which is great, but it fails the progress rule. What if P0 needs to get in 10 times in a row and P1 is just idle? Too bad. P0 is stuck waiting for P1 to take its turn, even if P1 has nothing to do. It's just too rigid.
Okay, so that didn't work. Let's try something a bit more flexible. In this approach, a process raises a flag, basically saying, hey, I'd like to go in. Before it enters, it just politely checks to see if the other process's flag is up. If it is, it'll wait. But here's the new problem. They can be too polite. Picture this. P0 raises its flag. Then, a split second later, P1 raises its flag. Now, P0 looks at P1's flag and says, oh, you first. And P1 looks at P0's flag and says, no, after you. They both get stuck waiting for the other to go. Again, progress is violated. Nobody gets anything done. So, what's the fix? Well, it turns out you have to combine both ideas. Processes still raise their flags to show they want in, but they also use that turn variable from our first attempt. That turn acts as the tiebreaker if they both raise their flags at the same time. And this simple combination, it finally works. It satisfies all three rules, but only for two processes.
But modern computers have hundreds, sometimes thousands of processes all running at once. We need a solution that can actually scale. And the inspiration for it? It comes from a surprisingly low-tech and, frankly, delicious place.
The solution is famously known as the bakery algorithm. And yeah, it works almost exactly like the beautifully simple and fair system that bakeries use to manage a crowd of hungry customers.
You know how it works, right? You walk into a busy bakery, you pull a ticket from that little red dispenser, you get a number, the person at the counter just serves whoever has the lowest number. What if two people somehow get the same number? Well, you'd probably use some other tiebreaker, like whoever has the shorter name. This real-world system is the perfect blueprint.
Okay, don't let this table scare you. The idea behind it is actually really simple. Each process gets a ticket number, just like in the bakery. Then, to decide if it's its turn, a process looks at everyone else's ticket. The rule is this: you can only go if your ticket is the lowest. And if there's a tie in ticket numbers, we use a unique process ID as the tiebreaker. This little pair of numbers, ticket number, process ID, guarantees that every single process knows its exact place in line. No ambiguity.
And just like that, by following that simple bakery logic, the processes create a perfectly clear order out of potential chaos. In this example, process P0 goes first with ticket number 3. Then comes P3 with ticket 4, then P2 with 7, and finally P4 with 8. What was a frantic race becomes a predictable, orderly, and fair sequence. So, what's the big takeaway here? It's that the seamless multitasking we all just take for granted is built on these invisible yet elegant rules. They turn what could be total digital chaos into a fair and stable system. This is what stops your bank account from getting scrambled, and it's a fantastic reminder that sometimes the best solutions to our most complex digital problems are inspired by the simple logic of the world all around us.
You know, when you start looking for it, you see it everywhere. From the traffic lights that manage intersections to the simple, unspoken rules of forming a line for a bus. These core principles of synchronization, of managing chaos and ensuring fairness, they are the silent organizers of our world, turning conflict into cooperation, both in our computers and in our communities.